Hello everyone. Now, with the idea of Morse circle and friction, we are well equipped to understand shear strength of the soil. Right? So, we'll start with the module number 4, which is titled as shear strength of the soil. Right? Part of basic geotechnical engineering, module number 4. So the contents of the module are this way: shear strength of the soil, concept of shear strength, more Coulomb failure criterion, modified more Coulomb criterion, total and effective shear strength parameters, factors affecting shear strength of the soil. Then we have thixotropy, sensitivity, and measurement of shear strength parameters like direct shear test, unconfined compression test, triaxial compression test, and field vane shear test under different drainage conditions. This is what we have to study. Obviously, if you have identified here, more is coming into picture, and because of that, more circle comes often in the discussion. So I think you have gone through all that Moore circle as well as shear strength concept, the probable plane of failure and impending motion, angle of obliquity, and then angle of friction, all that, right? So concept of shear strength is like that. We'll go into the details. Okay. So what is shear strength? The capacity of a material to resist the internal and external forces which slide past each other is known as shear strength. Now here there is a collapse of a building, right? So what has happened? Is it because of compressive strength, or is it because of tensile strength, or is it because of shear strength the buildings fail, right? So here you should appreciate that the necessity of studying shear strength of the soil is the soil failure usually occurs in the form of shearing along internal surface within the soil. The lab tests, and then there are many experiences say this, and all those things strengthen this particular statement that the soils fail because of lack of shear strength, right? Thus structural strength is primarily a function of shear strength. Okay, here the same when it is analyzed, right? It is like this: the foundation inside is shown over here. It is a strip foundation in the sense lengthwise it is more. If I have to show it in the third dimension, if I show it, it will be like this: a strip. The edge is over here, this wall is standing there, the height of the wall is there. Okay, so it is nothing but a strip foundation, right? So this is the side surface that is being seen here. Okay, now anyway, it has collapsed here on the left hand side. It has gone down, right, pushing the material over here. So what happens is there will be a slight bulge on this side, may be observed, may not be observed, but this will be shearing along this particular surface, right? It has sheared and then failed, right? So this opposite side arrows say that there is a resistance, right? Here opposite side arrows show resistance. These arrows actually which should be on this side, which will act on this curved surface, are nothing but shear stresses. The resistance offered is given by opposite These are applied shear stresses, and then the failure has occurred there. Okay, this is foundation failure. In case of embankment or landslides, you might have seen that the slopes come off, right? Again, it is not along a straight path, it will be a curved surface, and this is coming down, and resistance offered is opposite to that. So that is nothing but mobilized shear resistance, which is nothing but we will be calling it as shear strength, which is function of friction itself. Okay, we'll be seeing it shortly. Okay, significance of shear strength. Why civil engineer should study or should know the shear strength of the soil? The civil engineers must understand the nature of shearing resistance in order to analyze the soil stability problems, and where all the stability of the soil comes into picture. It is bearing capacity of the foundations, the slope stability, the lateral earth pressure on the earth retaining structures, and then the pavements, right? So these are the situations where we should know the shear strength of the soil. Okay, components of shear strength of the soil. Now this shear strength comes from where? Because of what? The soil derives shear strength from two sources. What are the two sources? The first one is cohesion between the particles, that is stress independent. It is not dependent on the stress, it is nature of the material itself, right? So cementation between sand grains or electrostatic attraction between clay particles, right? So this builds some shear strength. This is because of the cohesion. Another reason is frictional resistance and interlocking between the particles. That also brings resistance to the failure, which is stress dependent component. Now, if I show one particle there, another particle of soil touching this there, right? The two particles which are in contact. Now this soil particle has to move past this, means it has to slip off. Then whenever there is a tendency or applied force, there will be a resistance offered from the surface. That is nothing but friction, which we call it as now shear strength, right? This resistance. Now you know that this friction is a function of normal reaction. Now normal reaction is nothing but the force between the two particles, the force between the particles, between the two particles. If there is some force which will be trying to press these two particles one against the other, and then if the surface is trying to slip off, then there is a friction, right? So this friction comes as a function of normal reaction. Now by chance, if there is no normal reaction, this friction will not appear at all, because you know that this frictional force is given by N into mu, right? So next, now factors influencing shear strength are, okay, there are many factors which influence shear strength. Main titles are soil composition. The shear strength is affected by soil composition, then initial state of soil, and then structure of soil. Now in detail, if you want to write, soil composition means the mineralogy, we have already studied, grain size, small or big, grain size distribution, shape of the particles like angular, rounded, etc. Pore fluid means the water that will be there inside. Pore fluid type and content means whether it is viscous, non-viscous, right? Having unit weight, different unit weight, etc. right? And then ions on grain and in pore fluid. Ions on the grains in the sense in clay minerals, you have seen that negatively charged or positively charged, all those things. So such properties which make soil composition will affect the shear strength. Then another way, initial state. The state can be described by terms such as whether the soil is loosely arranged, the particles are loosely arranged, or the particles are densely arranged. When there is a dense arrangement, there will be a lot of contact surfaces. Because of that, there will be a lot of frictional force and a lot of shear strength that will be developed. If it is loosely arranged, in that case, there will be lesser number of contacts. Because of that, there will be lesser mobilization of friction. Because of that, lesser shear strength. Then there is over consolidated or normally consolidated. Consolidation will be studying as a separate module. You will come to know about that. Whether the soil is stiff, whether the soil is soft. So these are the conditions which will affect the shear strength of the soil. Next is structure of the soil, how the particles, it refers to the arrangement of the particles within the soil mass, the manner in which the particles are packed or distributed. Features such as layering or layers, voids more or less, pockets big or small, cementation tight or loose, etc. are part of the structure. So the factors which will influence the shear strength are all these. Okay. Okay, we have seen that stresses in soil will be because of gravity generates stresses, that is weight, force per unit area, that is weight in the ground at different points. Stress on a plane at a given point is viewed in terms of two components. Yeah, you know that already. We have been analyzing that. Whenever you have a surface and then some stress which is like this will be always resolved into a normal component which is perpendicular to the plane and the one which is tangential or parallel to the plane. Obviously these two components make this as the resultant stress, right? So if you remove inclined stress, you can have a normal stress sigma and then a shear stress tau. This is represented by sigma or sigma normal n, and this is general sigma, right? General shear stress. Sigma n is preferably normal reaction, or even sigma is also used, right? Here it is said sigma normal stress acts normal to the plane and tends to compress the soil grains towards each other. Okay. Sorry. So that here we are considering two surfaces which are in contact. Now if I say one particle is like that, another particle is like that, and then you are trying to push this off, right? And there is some intergranular pressure that will be acting, which we call it as effective stress, and you are trying to move it off, there will be shearing resistance, right? Shear stress represented by tau acts tangential to the plane and tends to slide the grains relative to each other. Distortion and ultimately sliding failure occurs. That's how it is. Okay. Okay, Coulomb's failure criteria. There are two names, Coulomb and Moore. The first person is Coulomb. What he said, his statement, and because of his tests, what he could find and put the hypothesis as the shear stress at failure is a function of normal stress. So shear stress at failure, which generally we call it as shear strength. Shear stress at failure, we term it as shear strength, and when we name it as shear strength, the suffix for tau would be F. If it is without F, then it is plain shear stress. Make sure of this suffix. This suffix is very important, because whenever we say shear strength, we put that F as a suffix, and then if you are trying to tell it as a shear stress, it is without that suffix F. And we say, the Coulomb says that shear strength is a function of normal stress. How that function is, that is not the point of discussion at the moment, but it is dependent on normal stress. That is what the Coulomb said. Then Moore came into picture. Moore failure criterion. What it said, Moore presented in 1900 a theory of rupture of materials. That was the result of combination of both normal and shear stresses. So what is that theory of rupture? It is combination of normal. Here it is only normal stress. The Coulomb's theory says that it is only dependent on sigma, the normal stress. But he said it is not only just normal stress, but it depends upon shear stress also. The shear stress at failure is thus a function of normal stress, and the Moore circle is tangential to the functional relationship given by Coulomb, right? So the similar function given by Coulomb, but there is a condition that there is a particular combination of tau and sigma which will be making that plane tangential, or that stress tangential to the Moore circle. You have already seen in earlier videos. Now combination of Coulomb and Moore gave rise to the Moore-Coulomb failure criterion. What it said, this theory states a material fails because of a critical combination of normal stress and shear stress, and not from their either maximum normal or maximum shear stress alone. Yeah, appreciate the earlier slide statement. I have said exactly the same thing, that in the Moore circle, more normal stress or more shear stress will not give you a failure condition. What is the failure condition? It is a particular combination of normal and shear stress which will make such a combination that angle of obliquity is maximum, or it leads to what is known as angle of friction. Okay, that is what is Moore-Coulomb failure criterion tells. Okay, now the same statement I have made it there, and then here it is represented by a functional relationship. Now if I draw or represent x-axis as normal stress axis and shear stress axis there, right, there is a line which is represented as Moore-Coulomb failure criterion, Coulomb, some mistake in spelling, Coulomb, right, Coulomb, Coulomb, right, Moore-Coulomb failure criterion. So that is the one which is making an angle of phi with horizontal, which we call it as angle of friction. And because it is between soil and soil, that's why it is called angle of internal friction. And the intercept on y-axis is represented as cohesion, or C. Right? So actual failure, Moore failure envelope is like that. Means here if you take any point below this dotted line, I'll show you some points. For example, if I take point A, it will have a normal stress so much, a shear stress so much, but this is leading to an angle of obliquity, you can just join here and then see angle of obliquity lesser than phi. Because of that, the failure is not there, or there is no probability of failure. So all such points, if you take and then cover them all, you get this dotted line. So it is covering all of them. That's why it is called envelope. It covers all the safe conditions. And then when you come to a point B on the line, dotted line, it is a critical combination where the failure is feared, right? And then if you go beyond that, if you try to analyze C, the C never exists, because the moment if it goes beyond B, anywhere here, the shear stress is slightly more, the shear stress is slightly more than the critical combination, the failure will occur. So there is no point to go ahead. Try to understand that. So below this particular dotted line, you got all combinations which are safe. On the line, it is all critical combination, and beyond that, you don't get any combination at all. Now this is actually a quadratic line, but it is approximated as a straight line like that. And the equation of this straight line, equation of straight line y, this is y equal to mx plus c. X is this, c is intercept, m is slope, which is tan phi. So that's why you get this equation. So although the failure curve is a quadratic function, the dotted line over here, it can be represented linearly as tau f, the shear strength, is equal to C plus sigma tan phi. C is intercept on y-axis, which is cohesion, and sigma tan phi. Tan phi is a slope, phi is angle of internal friction, and C is nothing but cohesion of the soil. This equation is known as Moore-Coulomb failure criterion. So what is Moore-Coulomb criterion? It is nothing but this equation. Shear strength is given by C plus sigma tan phi. So shear strength is given by cohesion plus normal stress into tan phi. Phi is angle of internal friction, C is cohesion. Now here, the cohesion C and the angle of internal friction phi put together are known as shear strength parameters, because these are the parameters on which the shear strength depends. C and phi. Sigma is a variable, and phi and C are the properties of the soil on which the shear strength depends. If sigma is more shear strength would be there, right? So it is directly proportional that way, and C and phi are the properties of soil. Okay. Further, here Moore-Coulomb theory can be put this way: the shear strength parameters, that is C and phi, though they are assumed to be constants, look at that, actually they depend on conditions of the test, such as drainage conditions, rate of strain, and magnitude of the normal stress. You can just see here it is bending, and as it is said in the earlier slide, quadratic. But more generalized the strength envelope about it. Also, it is known as failure envelope, or as a curve which becomes flatter with increasing normal stress, or it becomes normal parallel to the horizontal, but it can be assumed to be a straight line. We'll see further. That's how it is. Tau f equal to C plus sigma tan phi. Now, based on the values of shear strength parameters, that is C and phi, soil can be classified as, or referred to as, mainly. There are variety of ways. The first one is cohesion less soil, right, where C is equal to 0, the intercept on y-axis is equal to 0 on tau sigma graph, right? So if you find number of points, you fit in a curve, a straight line, and equation of the straight line would be tau f equal to sigma tan phi. There is no C here. This angle will be phi, angle of internal friction. The care has to be taken here that tau and sigma have to be plotted on the same scale, otherwise your phi gets distorted. Same scale has to be used for both the axes. Now one more, wherein the failure envelope or strength envelope becomes parallel to the horizontal, where phi is equal to 0 and C will have some magnitude. In that case, it is purely cohesive, we say. There is no frictional component here other than natural attraction between the particles, which is known as cohesion. So tau f is equal to C, the cohesion. Then the last one, which is referred to as C phi soil, what it means is it will be having both the values of C, the cohesion, and also angle of internal friction phi, and general equation of a strength envelope or equation of failure envelope would be tau f equal to C plus sigma tan phi. So that is general. If C becomes 0, that is this intercept becomes 0, it goes over there, right? If phi becomes 0, this becomes flatter. That's the particular cases. This is most general one. Okay. Now total strength envelope. Here, anyway, you know all this. That is an element, stress element, wherein on these faces there is sigma 1, and on vertical faces you have sigma 3, and there is a probable failure plane at an angle of theta. There is a normal stress acting on that. There is tau f shear strength or shear stress acting on that. And then if you plot the combination of sigma 1 and sigma 3 where the failure occurs, and then if I try to draw a more circle for a condition where the failure is about to happen, then I can plot sigma 1. It is over here. You can just see here, because there is no shear stress, so the point over here it will be sigma 1 comma 0. That is the point here. Similarly, this will be sigma 3 0. Sorry, and the two planes are perpendicular to each other. That's why these 2 points, sigma 3 point and sigma 1 point, has to be diameter. I can find out the center of the circle and then draw the circle. Likewise, you can apply different values of sigma 1 and sigma 3 combination and see that the failure condition is arising. So there is combination 1 with sigma 1, sigma 3. Second combination is taken, and then they have plotted a second Morse circle. And then if you try to draw a common tangent for that, because a tangential point is the point where the failure occurs, and common tangent, when you draw, you get an equation like this for this curve, that is tau f equal to the C, which is intercept on y-axis over there, this height is C, and this angle is phi. The same angle is shown over here, right? So tau f, the shear strength of the failure plane, is equal to C plus sigma n tan phi. Sigma n is normal stress, tan phi. So this is total strength envelope, in the sense sigma 1 and sigma 3 are the total stresses, not effective stresses. Now if you take effective stresses, in the sense
From sigma 1 you minus the pore water pressure, you will get sigma 1 dashed. Likewise, if you plot, means here you can just see this was sigma 1, I have subtracted u. Here this was sigma 3, subtracted u, and then the more circle bodily shifts by an amount of u on the left hand side. Similarly, the other circle also shifted. Now you draw a common tangent, right? Now you draw a common tangent, which is a dotted line over here. The equation of the line would be tau f equal to c dashed c prime plus sigma n dashed tan phi dashed. So whatever angle you get, this is referred to as effective angle of internal friction. This is called effective cohesion, and this is called effective strength envelope. Whereas the earlier plot, which is already shown here, it is called total strength envelope, right? Okay. Sensitivity. There is a property of the soil which is known as sensitivity. The consistency of an undisturbed sample of clay is altered even at the same water content if it is remolded. We'll go further, you will understand what it is meaning. It is because the original structure of the clay is altered by reworking or remolding. Since the strength of the clay soil is related to its structure, remolding results in decrease of its strength. The degree of disturbance of undisturbed clay sample due to remolding is expressed as sensitivity. Yes, this is the important point. The degree of disturbance of undisturbed clay sample due to remolding expressed by sensitivity. Now how it is measured? Okay, here you have got sensitivity is equal to cube u undisturbed divided by cube u remolded. Okay, this is a classification of soil based on sensitivity. If sensitivity is equal to 1, we say that it is insensitive. If the sensitivity, this ratio is coming out 2 to 4, then it is classified as normal to less sensitive, right? Then the structure of the soil may be honeycomb structure, and then 4 to 8, if the value comes out to 4 to 8, sensitive. Honeycomb structure or flocculent structure. 8 to 16 is extra sensitive flocculent structure. More than 16, we say that the soil is quick. Okay. Now, what this QU means, you will come to know afterwards that for shear tests in the laboratory, we conduct unconfined compression strength test, wherein we take a soil sample. You can just assume here this cross section is actually a cylindrical one, right? The diameter and height ratios is such that height is double the diameter, h is equal to 2d, that way. And then this soil sample is compressed this way without holding anything on the sides. Just a vertical sample is put in the loading frame and compressed till it fails. So that is called QU, that is unconfined compression strength, right? So this is for undisturbed sample, means the soil is taken in such a manner that the structure or the particle arrangement is not disturbed. Just like that, you bring it, test it in the form of a cylinder, then you will get some strength that is put in the numerator. Now what you do is you bring the sample of the soil, remold in this, in the sense disturb the soil sample, rebuild the sample by compacting in such a manner that the same density, same water content is maintained. But interestingly, what happens is when you test, it gets reduced. That is called QU remolded. So this ultimate value of soil at which it fails is known as unconfined compressive strength of the soil. Indirectly, it measures shear strength, but anyway, it is called, at the moment you take it as unconfined compressive strength. And this, now look at that, without disturbance, if you test, it is there. With disturbing the soil sample and remolding it to the same density and water content, it is there in the denominator. And this ratio goes on to a value 1 and more than 16 also. Interesting, right? When it is recompacted to the same density and water content, it loses its strength. That is what is sensitivity, right? The degree of disturbance of undisturbed clay sample due to remolding is expressed by sensitivity. What is sensitivity? It is a ratio of unconfined compressive strength before disturbance and then after disturbance, right? There are reasons why it happens. It is all these reasons, right? And the classification, depending upon the values of sensitivity, it is all this: insensitive, normal, sensitive, and extra sensitive. And then too much, then it will be quick. Okay. So here you can just see here shear strength, that is tau, is plotted on y-axis and time is plotted on this axis. Now look here, it is showing some shear strength, tau f rather, tau with a suffix, tau shear strength, right? And it is having some value, and then the same soil, when it is undisturbed, it is showing you this much of value of shear strength, and when it is remolded, the strength drops to this value. Suddenly you remold it and then check the strength, it drops. That is what we have said, that it is sensitivity. If I call it as 1 and then 2, the ratio of 1 to 2, the ratio of 1 to 2 is nothing but sensitivity. That is what we have seen. But interestingly, if you remolded sample, if you don't test it, you set it just like that, wait for some good amount of time, and then after some time, right, if you test after a little while, if you test it, you will see that it is not just 2, it is slightly more, 3, because shear strength is given by this level, right? So here it is there. Now in the sense, it is not decreased to the 2, it has gained a little bit of strength, and if you give a really good amount of time, it may so happen that the gain strength may come up back to a disturbed level, right? This gaining of strength when the time is given for the soil is known as thixotropy. So there are two things. When suddenly the strength is lost, it is known as sensitivity, but regaining of strength when you give time for the soil is known as thixotropy. Okay, thixotropy is an isothermal, no change in temperature, a reversible time dependent process which occurs under constant composition and volume. Thereby a material softens as a result of remolding and gradually returns to its original strength when allowed to rest. The larger the sensitivity, larger the thixotropic hardening. It's obvious, right? So with this graph, I think you can talk both about sensitivity, that is a drop, and regain of strength back to the normal as the time passes is known as thixotropy. Okay.